let's take a moment to talk about the force on a current carrying wire in a magnetic field, which is a topic I know you've been wondering about. So for starters, you know that the force on a charge, right here, is given by F equals QV cross B. V is the velocity of the charge in this case, or velocity is going to the right. B is the magnetic field going into the board. Remember, the X is into the board. To find the direction of F, oh, that needs a vector sign. I got sloppy, sorry about that. The direction is given by the right-hand rule. So remember, your fingers point in the direction of V, your palm or your fingers can curl, your hand should only bend one way. Keep in mind, right hand, in the direction of B, so point your fingers here, try to make your hand bend into the board or into the screen, and you notice your thumb points in the direction of F. But what happens if you have multiple charges? Right. Well, now, instead of Q just being the force per turning, now we need Q total. So Q total is just in the charge density per volume. A and L are your volume. So in Q per charge times volume, V cross B. Where in QA and V, this is, oh look, these are charges passing through an area at a certain speed, or charges passing through an area in a certain amount of time. This is just current. And then L cross B. But in order to get this, we need this L to be a vector, because current's not a vector. So we define dl to be a length of the wire, a little piece of length, in this case this little chunk right here, going in the direction of current. So in this piece of wire, dl points to the right. And we integrate, because we can do that now, to get the total force acting on that segment. So for practice, let's say we have this loop of wire that has this current I going through it counterclockwise. I is, well, it's purple, it's just current going through. And you know that your F, force, we'll just rewrite this, force equals the integral of I dl cross B. Keep in mind another way of writing this, if we're just interested in the magnitude of F would just be I lb sine theta. Theta being the angle between your magnetic field, B, and your little length segment, in this case, I. So take a moment, pause the video, figure out if any of them are 0 or if any of them are easier to figure out. 0 is pretty easy to figure out, by the way, but let's see. Okay, now that you've had a moment to do that, you may have noticed that inside 1, current is going to the left, B is going to the right. That is sine of 180 degrees between them, that's 0. They're also anti-parallel. Same thing down here. Well, not exactly the same thing, but I is going to the right, B is going to the right, that is 0. Sine of 0 is 0 degrees, or 0. Sorry, sine of 0 degrees is 0. Which means that F1 equals F3 equals 0. Okay, good. 2 sides done. Good on that. 2 more sides. We have F2. Let's do a quick right-hand rule. Point your fingers in the direction of current, which is down. All right, you get the force on this side is coming out of the board, and the force on side 4, okay, fingers in the direction of current. Curl your hand towards B, the force is going in. But the angles are both 90 degrees, so the magnitude of those forces is the same. So the magnitude of F2 equals the magnitude of F4, which equals I, A, B. Now keep in mind the direction, F2 is coming out, F4 is going in, which means this loop is going to rotate, it's going to spin. That exerts a torque. Remember Physics 1? That was a good time. Well, let's go back. Welcome back to Physics 1, where we had torque equals R cross F. R being the direction, or from the center to where the torque is applied. So if we're applying the torque on this one, side 4 we called it. Oh look, the force on that side was going to be I, A, B. And our direction for this, our R, is going to be half of B, because that whole side was B. So it's 1/2 B, AB. Now keep in mind that if we're looking at torque, which we are, that if you push this side into the board and this side out, those will cause this to rotate in the same direction. So our total torque is going to be equal to 2 times that. Oh, look, those 2's cancel out, and we are left with torque on the current loop equals I, your side lengths, times B. Length times width. That looks familiar. We're going to call this area, so we get IA B, area of the loop. Now this, we defined it for a square, but it works for any type of loop. Shape, circle, oval, pentagon, whatever, world's your oyster. Figure it out. Now this is just the magnitude. The direction of this is such that it is going to align the loop with B, with your magnetic field. That's pretty important. Now let's take a look at what we can do with this. And the first thing we're going to do with this is rename it. So physicists like things that are pretty easy and compact and, they look good, right? Now we also know that we lost a lot of direction. We still want to get this torque equals some form of something cross something else. B has a direction, and then we're left with this weird front part right here. So what we do is we define this as mu, the magnetic moment, which is defined as the current passing through an area. So mu is just IA. Now another way of looking at this is your area is a vector. How do you know the direction of area vector? Oh wait, you guessed it. Right hand rule again. Now this is a modified right hand rule. So place your hand so that your fingers wrap around the loop with I. Loop with the current. If you're looking at this, it should be the bottom of your hands on the screen and your fingers curl with that. And you'll notice that you point out of the board. Your thumb points out of the board. So mu, in this particular case, points out of the board. All right? So curl your fingers with the current, and your thumb tells you which way you're going. And that's how you get your direction of mu. So now that we have this mu, this magnetic moment, what to do? Well, we use it actually to say that the torque, that should be a vector, sorry, the torque aligns mu and B. It'll shift. It's not unlike what we did with the dipoles in the last chapter, the electric dipoles, except instead of an electric field, now we have a magnetic field. Instead of the electric dipole moment, we have a magnetic moment. So let's calculate the torque and potential energy of this loop below. We didn't talk about potential energy yet, but we'll describe it here in a second. So starting off with this, you know that torque is going to be equal to mu cross B, where all those are vectors. Mu is simply IA, the magnitude of mu, which is our 2 milliamps, 0.002 amps, times our area. It's a circle, so that's pi times 0.02 meters squared, which is roughly about 2.5 times 10 to the minus 6. 2.5 times 10 to the minus 6 amp meters. Crazy unit, but it'll do for the time being. So then, if we want to find torque, I would say that this is mu B sine theta. Theta is 30 degrees. So this would be mu being 2.5 times 10 to the minus 6. 2.5 times 10 to the minus 6. B is going to be 0.5 teslas, Tesla being the unit of the magnetic field, sine 30 degrees, which is equal to 6.3 times 10 to the negative 7. 6.3 times 10 to the minus 7 Newton meters. Here, I'm going to write this up here. Torque is equal to 6.3 times 10 to the minus 7 Newton meters. Let's take a moment to talk about energy. So we have this current carrying loop in a B field. This loop has magnetic moment that points in the same direction as the area vector of the loop, and this loop will experience a torque to align it with this magnetic field. So this loop right here will feel a turn like, and this one right here will feel another turn to align this down here. So it's kind of like a mousetrap. If you put your loop here, it'll start to rotate. If you put it here, it'll rotate. It's kind of like a little spring. If you put it here, it'll just stay the same. So what we need to do is figure out how much energy is stored just in the alignment of this magnetic moment and this B field. So let's take a look at potential energy, and we know that work is equal to torque d theta, and there's a dot product there, but torque always goes in the d theta direction. Way to look at this, if this is R, you put some force here, torque would be, well, let's see, R cross F, the torque's going to be coming out at you, and it is going to rotate that. So it'll start to spin. The torque will cause things to spin, which is the theta direction. Spinning is theta. All right. We also know that work done is equal to minus potential energy. So if we're going to rewrite this, we'll get U, I'm going to move the other thing, torque, how do we write torque now? We write it as mu. I'm going to go ahead and write this as mu b sine theta. We'll just deal with magnitudes. D theta, which equals mu b negative cosine theta. Oh, do we have any other way we can write this? Well, we sure do. We can write this as minus, let's get a different color real quick, minus mu dot b, the dot product. So let's take a moment and look at the energy of these configurations we've drawn and one extra one. So if we look here, mu dot b, mu b cosine theta, here they're aligned. Wait a minute. This one in the middle here looks a little different because we know that cosine of 90, this corresponds to u, for this case, is equal to 0. Interesting. But let's look at this one right here. Over here, we have them aligned. Wait, what's cosine of 0? That's 1, but this negative sign here would mean this would be negative mu b. And then if you come over to this right side where they're anti-aligned, this one would actually be minus mu b cosine 180 degrees, which is just mu b. And it's potential energy. So all you care about when you look at potential is just the change in potential energy. It doesn't really matter where 0 is. You can set 0 to whatever reference you want. And for ease, we set 0 equal to this middle case right here. So you have the most energy stored. This loop is going to snap back and flip pointing that way. This represents kind of a middle amount of energy, and this is no energy stored because they're already aligned. Now let's look at some practical applications of this. Now let's do something practical. Let's hook this current loop, and this connects to a battery, and it goes into a wire, and this wire is in a magnetic field created by a magnet. Yeah, okay. We're not shocked by that. But we'll notice the torque here, and there's a torque from here, the force acting on the side, and it causes this to rotate. So it'll rotate. Wait a minute, but will it stop rotating? No, thanks to this property called inertia, the wire loop keeps on going, and then it tries to align again. So it goes, it overshoots, it goes wing, it aligns, but it overshoots because it's got inertia, and then it just keeps on spinning, and spinning and spinning and spinning. So the things I want you to know, because this may appear on an exam, or not, but it might. When electric current passes through the coil in the magnetic field, it produces the force which causes the torque. This spins it, and then if you connect it to something like a tire, you can make your golf cart go. Or Tesla. I guess Tesla's a little fancier. It gets a spoiler. Ta-da! We'll put the little T right there. There we go. Alright, so I hope that helps. If you have any questions, let me know. See me in class, and I will talk to you later. Oh, side note, this little site, Hyperphysics, is a great site to kind of get the basics on some physics, so take a look in there too. It's a good pick-me-up. Thank you, and I will talk to you later.